Okay, let us, this is week 5. This is the asynchronous part of week 5. We're done with logistic regression, thank goodness. And we're actually done with the first half of the course. First half of the course is intended to get you up to speed on Stata, on basic regression principles. It was a frantic 5 weeks. And I apologize for that, but now you can reap some of the benefits of all the hard work that you've done so far. So now we're turning from just the mechanics of regression, both in terms of running regressions as well as understanding the kind of basics of how to interpret coefficients and things like that, to the fun stuff, which is how do we apply regression analysis in a way that's going to tell us something interesting about the educational phenomenon that we're interested in. I said early on that every regression is an experiment. I want to probe that idea for a little while. I said life is too short not to aspire to causal analysis. So under certain circumstances, regression analyses can be convincing causal analyses. So the question that you should be asking yourself, descriptive analysis is fine for kind of a preliminary stage, but at the end of the day, you really want to know about effects. You want to know about the effects of some policy or some skill or something on later outcomes for kids, right? And they could be things that are happening in schools. They could be things that are happening in families. It could just be within the child, looking at skill development over time. So you want to think of aspiring to having a regression analysis that is a convincing causal experiment. So how do we do that? One phrase that is used in thinking about that question, whether a given statistical analysis is a convincing causal analysis, is to focus on the identification strategies. What about that approach gives you confidence that you've identified causal effects? So we will talk about a number of strategies here. Identification strategies for causal effects. One obvious one we've already talked about is random assignment. If you have some treatment, some policy, some something that's changing an independent variable of interest, and it's correlated with outcomes, right? In the absence of random assignment, you've got problems because you can't be sure that the people who ended up receiving the treatment are different from the people who aren't receiving the treatment. Random assignment does that by randomly assigning people to treatment and control group. And what that does is to make sure that the relationship between receiving the treatment and the outcome is not contaminated by omitted variable bias, right? What random assignment does is to ensure that on average, the control group is virtually identical in all ways, measurable or not, to the treatment group, right? So the distribution of family backgrounds, the distribution of health status, the distribution of everything that might affect that outcome is balanced between the two groups, the treatment group and control group, because of random assignment. So that provides most convincing evidence on causal effects. because of this ability to get rid of potential omitted variable bias, you're balancing whatever unmeasurable factors there are between the two groups by random assignment. It's not perfect. Random assignment, sometimes when you flip the coin to get this treatment and control group, you're unlucky and you've got some imbalance between the two groups. You can do you can control for potential dimensions of unbalance, and that gets you closer to balance. But once you have evidence that you haven't really attained comparable groups, treatment and control groups, then you really don't know whether your adjustments for variables you can observe take care of all the bias. But for the most part, that's relatively rare, especially if you've got a fairly large sample. So random assignment provides the most convincing evidence on causal effects. What other identification strategies are there? Well, we have when we looked at the article that looked at adjusted correlations between parent income and child outcomes, child completed schooling, we took a regression-based approach to control for differences. All right, so if you think about it, we were interested in really the causal impact of family income on children's completed schooling. We related family income over 15 years of childhood to eventual completed years of schooling for kids. We tried to adjust the higher and lower income people. The experiment we're really trying to run is something like, suppose we could randomly assign $5,000 of extra income for families, let's say low income families with average income of $20,000, right? $5,000 more than that. We're relying on our regression line. This was family income and child ed. We're relying on our regression line, if this is 20,000 and this is 25,000. We're relying on our regression line to try to tell us what would actually happen if we had random assignment. And to get closer to random assignment, when we ran this regression, we put in a bunch of control variables, right? We controlled for family structure, we controlled for parent education, we controlled for race, ethnicity, we controlled for region, all sorts of things that might make the $25,000 family income kids different from the $20,000 a year family income kids. And if we could somehow measure all those potential differences and control for them, then we would be coming pretty close to random assignment. Random assignment balances the two groups through flipping a coin. Regression-based approaches try to balance the two groups, the $20,000 and $25,000 a year groups, using control variables. This, though, is not very convincing. Because of lingering omitted variable bias. Yeah. Right, you can control for a bunch of stuff, but you really don't know whether you've controlled for everything that's relevant in terms of distinguishing the $20,000 and $25,000 a year kids. So you can consider a regression-based approach, a well-controlled regression approach, to be suggestive of what the causal effect might be. But you certainly can't be as convinced that you've identified a causal effect as if you had random assignment. Okay, so those are the two most common approaches to identifying causal effects. For the next couple weeks, we're going to look into a third category of approaches. That are sometimes termed quasi-experimental. Relying on what are sometimes called natural experiments. So this is something that wasn't really part of most social science research until well into the 90s, when economists kind of caught the bug. It certainly wasn't invented in the 1990s, but it started being applied much more consistently in the 1990s. These kind of quasi-experimental approaches are largely unknown within most education research areas. They're rarely used in developmental psychology studies. So this will be somewhat novel to faculty that you're working with who aren't familiar with it. But it's very cool, and it's very, it can be very convincing. It requires rearranging your thinking. It's not, okay, I've got this big data set. I've got to think of all the control variables that I can. It's a different way of thinking about it. It's a way of observing and being on the lookout for things that happen that are producing variation in the independent variable you're most concerned about that is completely beyond the control of the people that you're studying. Okay, so the two studies that we'll be talking about next week, one is based on double dose algebra, which is a program that was put in place in Chicago schools 15 years ago or so. And it wasn't just rolled out in a way where teachers could volunteer to do double dose. It was required for all the kids who scored, this is in 9th grade double dose, whose 8th grade math scores were below the median statewide. So kids didn't have any choice about whether they went into double dose or not. If their 8th grade scores were below the 50th percentile, they got double dose. If their 8th grade scores were above the 50th percentile, they didn't. Now, it's not exactly the case that there was complete compliance, but it was a very, very sharp discontinuity, as it is called. And you can take advantage of that sharp discontinuity where the double dose was completely beyond the control of the students and their families, right? They were either there or not, depending on what their 8th grade test scores were. The other example is looking at the effects of pre-K, state pre-K programs, because in a number of states, being able to get into pre-K was determined by birthday, right? So let's say the cutoff is September 1st. If you're, say, age 4, by September 1st, you get in or you're offered a slot. If your birthday comes after September 1st, you're not offered the slot, right? So the kids and their parents had no control over whether they could get in or not, or whether they would be offered a chance to get in or not. because they had no control over their children's birthdays, essentially. So those are examples. These are regression discontinuity approaches. Regression discontinuity approaches. That's this coming week, week 6. Week 7, we'll look at approaches called difference in difference. Where you compare two groups before and after some event happened. Sometimes you have a triple difference, difference in difference in difference. We'll talk about all that. And a subset of these take advantage of what's called fixed effects. For example, there are sibling fixed effects models. I don't want to get into the details of explaining what those are about, but there are a couple of things we'll be reading where, again, things happen that are beyond the control of the people being studied, where you can take advantage of that to estimate impacts. One of my favorites is a study by Janet Curry that looks at the effects, wants to know the effect of auto pollution on low birth weight. Okay, so that's tough because pollution, where people live and whether they're close to a highway or not, is a function of a lot of things. And if you just compare people who live near highways with people who don't and look at the birth weight of the children born to those families, there's a lot of confounding there, right? So she was able to take advantage of the fact that that both New Jersey and Pennsylvania rolled out an Easy Pass program for their toll roads. So Easy Pass, it used to be the case that every single toll road that you went on periodically had these booths where you would drive up, idle your car, give money to the attendant, you'd get change or not. But every car had to stop and idle for a while this transaction was being made. Easy Pass, of course, gives you a little sensor and there's no stopping at all. So an area where there had been toll booths was converted to an area where there was Easy Pass. And the amount of pollution generated around that area was dramatically less after Easy Pass came in relative to before. All right, so you can take advantage of that fact and compare what Janet Curry did, would-be mothers' birth weight of moms before and after the Easy Pass came in, and comparing not only before and after, but also between women who were within 5 kilometers of the toll booth versus 5 to 15 kilometers from the toll booth, right? So she could mix in distance and timing to see if there was any effect, and lo and behold, there was an effect. So again, there the people had no control over the fact that this Easy Pass system was being rolled out. You could imagine people over the longer run changing residence based on all of this, but in the short run, they one day had substantial pollution in their neighborhoods, and the next day they didn't. So that's another example of a difference in difference kind of analysis. Another that's a very nice example, there was an enormous earthquake in Chile in, I think, the early 2000s, maybe late 1990s, where the researcher was interested in the effect of maternal stress for pregnant women on birth weight and educational attainment and so forth. So earthquakes, as we know, are very unexpected. They had very severe effects near the epicenter. And as you go away from the epicenter, they had smaller and smaller effects. So you could take advantage of that by looking at birth weight and by looking at eventual educational attainment for kids who were in utero either before the event or right after the event. And you could do that comparison. You could do the comparison between before and after for the kids who are most affected, closest to the epicenter, versus some distance away versus some other distance away, right? So if the earthquake was causing stress and prenatal stress, and if that affected kids, you ought to observe this kind of graded relationship where the biggest effects were right after the earthquake, very close to the earthquake, and it ought to get smaller and smaller as you move away. So again, that's another example, but in that case, again, it's not that you've got a data set and you want to try to do something with it. It's you've got an event, double dose algebra, earthquakes, rolling out of easy pass. You have an event, and then you try to assemble data that will enable you to take advantage of that event in order to determine what the impact of that event is on the outcomes of interest. So that's a preview of what's coming up. So let me set the board up and pause here for a second. Okay, so let's turn to an example now, regression discontinuity. And I'll try to set up the Cortez and Goodman article, which is that double dose algebra example. So the basic idea behind regression discontinuity is to find some interesting event that disrupts what would otherwise be an unremarkable correlation. So did some interesting event disrupt what would otherwise be some unremarkable correlation? In this case, the unremarkable correlation is between 8th grade math score and 9th grade math score, right? There are other dependent variables, 10th grade math score, 11th grade reading score, completing high school, going on to college, right? A whole set of things you can get from administrative data. But let's just stick for purposes of illustration to the dependent variable that's 9th grade math score. All right, so let's suppose we don't have any double dose and we just have data on math scores of 9th graders and math scores of 8th graders, right? This is the end of 8th grade, this is the end of 9th grade. Okay, so in the absence of double dose, there's going to be a scatter of points, but a pretty positive correlation. Kids who scored high in 8th grade on math are most likely to score high in math in 9th grade. So no big deal, that's unremarkable. But what makes this interesting is that an event came along, namely that double dose algebra was offered to 8th graders scoring below the 50th percentile in 8th grade. So it turns out to be convenient to recenter the data so that 0 is the 50th percentile. All right, so we've just taken 0 to 100 and changed it to minus 50 to plus 50 in terms of percentile. It turns out, remember all the problem we had interpreting the constant? When the constant was projected way beyond the scope of the data. When we center it like this, this really isn't the y-axis. The y-axis comes here. This is the 0 point. And we won't have to worry about any sort of projection beyond the sample because it's right in the heart of the sample, 50th percentile. So let's suppose that everyone scoring below the 50th percentile in 8th grade gets this double dose of algebra, 2 periods instead of 1 in 9th grade, and that everyone above the 50th percentile just gets normal 1-period algebra. The double dose program was implemented pretty well. They set it up so it was the same teacher teaching both math periods, and the curriculum across the 2 periods was tightly coordinated. So in effect, it was like a double dose, right? Twice as much exposure to algebra as was normally the case. So think about what we would expect if double dose came in and was offered universally to all children below the 50th percentile. Well, if it was effective by the end of 9th grade, the test score should be much higher than it otherwise would have been. So we'd expect everyone to the left of the 50th percentile to be, we still expect the positive correlation, but you ought to have this displacement, this vertical displacement of the level of achievement, with it being higher because of the virtues of double dose. And of course, once you hit the 50th percentile, that all goes away because kids above the 50th percentile didn't get double dose algebra. All right, so what we'd expect would be lines that look something like this. And what we really want to know is what the jump is right at the discontinuity. All right, if you think about it, we want to approximate an experiment. And a kid at the 49th percentile in terms of 8th grade math is going to be very similar to a child in the 51st percentile. But they're going to differ because one got double dose and one didn't. So we know most about what the impacts are right around the 50th percentile. And the challenge is to figure out what is that effect? What is, by how much did the line jump up right at the 50th percentile? Well, that's a pretty straightforward regression task. We can do a regression of 9th grade math equals A plus B1 8th grade math. Right, that's a single line. That's the black line, including the dash part of the black line. But now we want to allow for the constant to change for all the kids who receive double dose. Right, so if we really expect these lines to be parallel, and we'll talk about how we handle if they're not, all we have to do is, think about it, all we have to do is add something that's going to change the constant, jump it up. This is the A point, right? It's the point at which 8th grade math is 0. We scaled 8th grade math, so the 0 point is corresponds to the 50th percentile. Now we want to allow for the regression line to jump up in the case of kids scoring below the 50th percentile. So I should pause this and let you think about it, but all we have to do really is add a 1, 0 variable for whether double dose, i.e. whether 8th grade math is below the 50th percentile. All right, so we saw these 1, 0 dummy variables with when we were looking at race ethnicity. And if you play out the same, what does this look like for different groups? For above 50th percentile in 8th grade, this equation is 9th grade math equals A plus B1 8th grade math plus 0. These people are all above the 50th percentile, so they're all taking values of 0 in that variable. All right, so that A is going to be this intercept point right at x equals 0. And B1 is going to be this slope. All right, so for below 50th percentile in 8th grade, we've got 9th grade math equals A plus, and now we're kicking in the values of 1 for whether double dose, because they all got double dose. They didn't all get double dose, but we're assuming that they did for now. So they're all 1s, so this just becomes B2 for those people. Everyone below the 50th percentile is getting B2, so the constant term isn't just A, it's A plus B2 plus B1 8th grade math. So in this case, we're forcing, because we didn't put in that interaction between 8th grade math and whether double dose, we're forcing the slopes to be the same, right? That B1, we're forcing it to be the same for the two groups. So these two lines have to be parallel to one another, but we're allowing the constant to change by B2. So B2 is the effect of double dose on 9th grade math. Is that a causal effect? Well, you have to ask how convincing it is as a causal effect. And as I tried to argue before, whether you're at the 49th or the 51st percentile, is a pretty fluky thing. Kids at the 49th and 51st percentile are going to be very similar, except they're different in slight ways in terms of their math achievement. So that's a pretty good, something close to random assignment. So this effect, which is B2, which is the amount that the line shifts up, is not a bad causal estimate of the effect of double dose on 9th grade. And if you keep going, you can really plug in any outcome you want: 10th grade math, 11th grade math, ACT, verbal scores, high school completion. This equation with these different dependent variables is going to give you, with B2, assuming things are parallel, a pretty solid causal estimate of what the effect of double dose is on all those outcomes. All right. Too bad we're not interactive here, because I'm sure there are some questions, but maybe we can talk about those when we do the double dose paper in a week. All right, so that's when the lines are parallel. There's nothing that guarantees that the lines are going to be parallel. Okay, so this is still the line if double dose algebra weren't around. But it could be that double dose had stronger and stronger effects the higher the percentile score up to the 50th percentile in 8th grade. Okay, I mean, of course, kids at the 49th percentile compared to the 1st percentile are going to be scoring higher in terms of 9th grade math. But the question here is the impact, is the shift going to be parallel, or is it going to be, say, not parallel? And this is not parallel in a way where the impact of double dose math is biggest for the kids who are very close to that 50th percentile cutoff. Could be the opposite. Double dose could have its biggest effect on the very low achieving kids, right? We don't know. But the point here is, how can we get around this assumption of parallel lines to allow for the fact that that red line might not be parallel? And we've seen an example of this already when we talked about dummy variable interactions. All we have to do is estimate this 9th grade math A plus B1 8th grade math plus B2, this is a B2 10 variable weather double dose. Which is to say whether they qualified because their 8th grade math score is below the 50th percentile. It's just a 10 dummy variable. But now we want to add in B3 and the product of weather double dose times 8th grade math. All right, exactly the same as when we did our dummy variable interactions. And how does that work? Well, you know, I still, when I see an interaction, I still just go back to the drawing board and I say, well, what does it look like for the above 50%, 50th percentile? Well, that's going to be 9th A plus B1. Let me drop this down a little bit. So above 50th percentile in 8th grade, we're going to have 9th grade math equals A plus B1 8th grade math plus 0, because these people didn't get double dose, plus 0, because this product is going to be 0. 0 times anything is going to be 0. So this black line, just as it was over here, is the relationship for untreated, which is to say kids didn't get double dose kids. And we're really fitting it to this portion of the line. Now, below the 50th percentile, we're getting 9th grade math, A plus, and just as before, we had the shifting of the constant, B1. We've got that, no, I'm sorry. B2 up here, right, is the shifting of the constant term. So the new constant term is A plus B2, that's the same. But now the coefficient on 8th grade math is B1 plus B3, which is all these people become ones. So we've got B3 times 8th grade math and plus just 8th grade math with B1 plus B3. Times 8th grade math. Again, this is exactly the same as what we did last week when we were looking at dummy variable interactions. So now we've got lines with different heights and different slopes. You know, it might be that B3 is statistically insignificant, in which case they're effectively parallel. But by including that interaction between being in double dose and 8th grade math, we're allowing for different slopes. And we're really allowing for different slopes only to get the optimal estimate of, again, B2, which is the shift in the constant, the intercept associated with being in double dose, right? That was true before over here. And now we're allowing for different slopes, and it's still true. We don't really care what the different slopes are, but we care about allowing for a different slope so that we get the best fit right around the 50th percentile, right? We don't want to force this thing to be parallel if in fact it's steeper or if in fact it's flatter. We want to allow that to be, to just go with the data, find the best slope in order to give us at this cutoff point, the 50th percentile, the best possible estimate of B2. And B2 is the effect of double dose on 9th grade math. So B2 is, again, the effect of double dose on 9th grade math, or 10th grade math, or 11th grade math, or 11th grade reading scores, whatever you want to plug in for the dependent variable. Now, things are never as simple as this. There are a number of small complications. This is the basic idea. And I want you to carry away the basic idea here. I mean, in fact, some of the kids below the 50th percentile didn't get double dose math. Some of the kids above the 50th percentile did get double dose, but there are ways around that. So you'll read in the article that instead of a 0 and 1, you didn't get it, you did, you jump from about 20% up to 60%, right? But that's still a big jump. And you take advantage of whatever jump you've got, and it's a big jump, which is good, to run these regressions. That's kind of a minor complication. A more substantial complication we'll talk about when we talk about the article. This is the most straightforward way to estimate the impact. There's a alternative way called instrumental variables. That takes advantage of the discontinuity and is just a little more sophisticated in coming up with this estimate of what B2 is. So we'll talk about that. But what I want you to learn first and foremost is the intuition where we don't have those complications. In the Wong and Cook and Barnett article, you have these birthday cutoffs, which provide analytic leverage to estimate the effect of state pre-K programs on achievement. In that case, this applies very directly. You've got a test score from kids who just completed a year of pre-K and kids who are about to begin the year of pre-K. And again, if you compare kids, let's say the cutoff was September 1st, if you compare kids with birthdays in the last week of August to the first week in September, you've got pretty comparable kids. They differ only in terms of their birth dates, and they're very similar in age. And in their case, they do an instrumental variables analysis, but the basic analysis is done this way. So I want you to understand how regression analysis can be applied to circumstances that come along, interesting events that disrupt what would otherwise be an unremarkable correlation, right? In this case, we had this pretty unremarkable positive correlation, and the event of double dose came along and enabled us to identify the impact of double dose right around the point where people were just in the program or just didn't get into the program. So there are many, many applications of this for education. So I think it's important to not only be able to read the literature that relies on regression discontinuity, but you know, in your own work, think about whether there might be opportunities to apply this kind of analysis. As I say, if you're taking a standard kind of data set, ECLSK, there aren't very many examples of regression discontinuities you can do. But as you observe what school districts are doing, you might have an occasion where they try out a program and do it on the basis of some past measure like achievement. They might, a state might roll out its pre-K program based on a birthday cutoff. So there are a lot of opportunities for regression discontinuity analyses that come up if you just have your eyes out for them. One of the more minor assignments that we're going to be getting to in a couple weeks, I guess, is this first paper. And the first paper is really just a one-page paper And I'm asking you to dream up a regression discontinuity design or a difference in difference design that provides a natural experiment and enables you to conduct a causal analysis, right? So it can be something that's really out there that you might actually investigate at some point. It might be something that you make up, some scenario, that's fine. But because this way of thinking about natural experiments is so different from the normal way we think about approaching data and doing analyses, it's very useful to get you to spend a little time thinking up a natural experiment on a topic that interests you that would enable you to approximate causal effects. All right, so that's intended to set you up for a week. This is Sunday, from a week from tomorrow. Tomorrow's logistic regression, and I apologize. It's the last. It's the last complicated, not very rewarding thing that we've got to go through because it's used all the time. This stuff's cool. Logistic regression, not so much. All right, see you tomorrow.